Hey guys, in this video we're going to look at the idea of molecular polarity. We're going to relate it back to our bond polarity that we talked about in the last module. So combining the idea of Vesper and bond polarity into determining the polarity of an overall molecule. So we're going to use Vesper and bond polarity together to determine whether or not a molecule is polar or nonpolar. And we're also going to look at our shapes and our bond dipoles to determine our overall molecular dipole if we do have a polar molecule. So let's just review what bond polarity is. Here we have a polar bond. If the atoms in the bond have an electronegativity difference of greater than 0.4 on the Pauling scale. So that results in a polar bond. And unlike a nonpolar bond where you have your electron density evenly distributed throughout your atom, with a polar bond, you're going to have your electron density, and this is in terms of an electron density map, more of your electron density of that bonding pair will spend its time around the more electronegative atom, and that causes us to have a bond dipole, where we call this bond dipole a vector dipole, which has magnitude and direction. As a note, this is not going to be exactly the same as a regular vector. Regular vectors are going to point to the positive. Someone was clever and decided to put the positive end, so write this little positive right here. So they drew a dipole, a vector in the opposite direction. So polar bonds, these are going to have an uneven distribution of electron density between the two atoms. And this causes partial charges to form. We're going to have a partial positive on the more electropositive atom and a partial negative on the more electronegative atom. So in the case of HF, we'd have a partial positive for our hydrogen and a partial negative for our fluorine. In the case of H2, there is no electronegativity difference between two hydrogen atoms, so they're going to have a perfectly nonpolar bond. Okay, so whenever we have this polarity, this is the idea of having poles. So a positive and negative pole. And as such, it kind of acts like a little magnet. Where positives will like negatives, negatives will like positive. Okay? If we have a polar molecule, we are going to have a net dipole in the molecule itself. Okay? Keep in mind we're talking about a vector quantity. So if we have two vectors equal but opposite directions, they will cancel each other out. And when you have symmetric molecules, that's what happens. So symmetric molecules bond dipoles cancel out. The vectors themselves cancel out. If we have a asymmetric molecule, we don't have those bond dipoles cancel out. And that results in a polar molecule. So we have an overall dipole for our molecule. And these will have a center of negative charge and center of positive charge. So we will have poles. Right? The negative charge and positive charge cannot overlap. If they do, then you have a nonpolar molecule. So let's look at kind of a mini chart, and I have a much more in-depth chart. We'll look at it again, but we're looking, does the molecule contain polar bonds? If the answer is no, we will always have a nonpolar molecule. If the answer is yes, are the polar bonds arranged symmetrically? If the answer is no, we have a polar molecule. If the answer is yes, then we have a nonpolar molecule. So it has to contain polar bonds, and you have to have asymmetry in order to have a polar molecule. Our polar molecules themselves, they are going to have an unequal sharing of electrons. They're going to have a center of positive charge that doesn't overlap with the center of negative charge. And these charges are coming from the dipoles, right? So these poles act like a magnet, like magnetic poles, where positives will be attracted to negatives, negatives attracted to positives. Our polar molecules, these are going to be things that are considered hydrophilic. They're going to be water-loving. As water is a highly polar molecule due to polar bonds and asymmetry. Okay. With our nonpolar molecules, we have equal sharing of electrons or an overlap of the positive and negative charges. So we get no overall dipole. Okay. And these are going to be considered hydrophobic in nature, which is what we call water-fearing. So water is a classic polar molecule. Oils and fats, generally considered nonpolar, which is why they don't really mix, right? Okay, so let's look at what I mean by that center of positive and negative charge. Right here, we have a molecule of carbon dioxide. And right here, we have a molecule of water. So carbon dioxide does have a distribution of charge within it. So it has a molecular dipole going towards each of the oxygens. So this one right here and this one right here. Maybe you noticed it, maybe you didn't, but these two vectors are equal but opposite directions, so they will cancel out. But we can also look at it in terms of kind of averaging out where our positive and negative charge is. We have a negative charge here, and a positive charge here. Our negative charges are going to average in the center. Our positive charge is going to average in the center. So they are going to overlap between our positive and negative. So that overlap of that positive and negative cancels out polarity. Okay. Water, on the other hand, it has dipoles going in this direction and they will combine to give us an overall molecular dipole like this, where we have positive charge here, negative charge here. So just real quick, erase this, just so I can make it a little bit more clear. So here is where we would average that positive charge. Here's where we would average that negative charge, and they are in separate places. So we get a partial negative area and a partial positive area that don't overlap. So this is a polar molecule. So vectors don't cancel. Okay, so that's very important to notice. Because of the symmetry of CO2, our individual bond dipoles are going to cancel out. Because of the asymmetry, and notice when we think about our molecule of water, it has lone pairs of electrons around the central atom. That's pretty indicative of asymmetry. Not always, but usually. But that's going to cause us to have a polar molecule. And we think about the properties between the two of these. Carbon dioxide is a gas at room temperature. Water is a liquid at room temperature, despite the fact that carbon dioxide is a greater molecular weight than water. So because of that polarity, it causes those molecules to hold on together much better, so it'll be more likely to be in liquid state at room temperature versus being in the gaseous state that we see in carbon dioxide. So the polarity really has a significant effect on the properties, the physical properties of the material itself. Polar molecules are going to have higher boiling points, higher melting points, versus nonpolar molecules with similar molecular weights. Okay, let's just real quick look at tetrahedral molecule substitution to kind of see this in action again. So here we have CF4, here we have CH4. A carbon-fluorine bond is highly polar, a carbon-hydrogen bond is nonpolar, but here we have a nonpolar molecule. And the reason this is because our bond dipoles cancel out. So if we look at this structure right here, all of our bond dipoles, they're symmetric around that central point, so they will cancel each other out. And we can also look at it in terms of where the positive and negative charges. So if this is our negative charge, it equals out to the center, right? So it's going to average out to the center. And then our positive charge is also going to equal out to the center, canceling out both of those charges, so there is no charge separation. But as soon as we substitute either a fluorine for a hydrogen or a hydrogen for fluorine, we produce a dipole. Okay? And the magnitude of that dipole is going to be based upon how separate that charge is. The more separate you can get that charge, and the greater the magnitude of that separation of charge, the greater that dipole will be. Here is just a flowchart you can use to determine if you have a polar molecule or a nonpolar molecule. And as long as you follow through with this, it should work out just fine. So, of course, the first question you ask is, does the molecule contain polar bonds? No matter what the symmetry, if you do not have polar bonds, you cannot have a polar molecule. Every time you have nonpolar bonds, you have a nonpolar molecule. Next, if you do have polar bonds, you have the ability to have a polar molecule, but not necessarily. So next, is a shape symmetric in all three directions? If the answer is no, that's going to be bent, trigonal pyramidal, seesaw, T-shape, and square pyramidal molecular geometries. If you have one of those molecular geometries, you have what's considered an asymmetric shape, and you will have a polar molecule. If you have polar bonds and an asymmetric geometry, you have a polar molecule. If you have one of our molecular geometries that are considered symmetric in nature, that's going to include linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar. All of those are considered molecular geometries that are going to be symmetric in nature. These, as long as your peripheral atoms are the same, you're going to have a nonpolar molecule. So all of your peripheral atoms, if they are all the same atom, you will have a nonpolar molecule. If you have substitution, If one of the atoms is not the same as the rest of them, then you're going to have a polar molecule. And that is everything for molecular polarity. I will talk to you guys in the next video.